at the University of Liverpool, and I'm very honored to give the first talk today and to get to tell you a little bit more about p-hacking and the simulation studies that we did of it. So I am a researcher in psychological methods. That means I try to find out what would be good methods in psychology, the statistical methods, but also experimental methods. So my approach to the topic was from a statistical and a methodological perspective. However, I won't bore you with any formulas today. This is very applied. So everything, like most of what I'm going to talk about today is based on this paper. It's called Big Little Lies. We were very proud of that title. A compendium and simulation of p-hacking strategies. I put the link to this paper here. I recommend, if you want to read the paper, read the preprint rather than the paper, because they fucked up our graphics. So the figures look better in the preprint. This is my collaborator, Felix Schönbrot, from LMU Munich. He was also the co-supervisor of my PhD thesis. So the work that I'm presenting is work that we did together. Now, to start with, what is p-hacking? Why are we here? So I guess all of you are here because you want to be good scientists. I hope, at least. You want to do transparent, honest science. You want to be innovative. You want to conduct ethical, thorough research. You want to be good colleagues, good scientists, good mentors, all of that. And, well, you don't want to be this. You don't want to be the bad scientist. Sam already talked about fraud and academic misconduct, sloppy science, unethical science, intransparent science. So there's like a clear bad side to things. What I'm going to talk about today is kind of in the middle. So it's like the ugly scientist. I'm going to be talking about a questionable research practice called p-hacking. There are also other questionable research practices, such as harking or salami slicing or overselling, and all of these are kind of like in the gray area of science. So they're obviously not good, but they're also not quite as bad as, for example, fraud, because they might just happen accidentally, unintentionally. And to give you an example, I brought you a quote from Brian Wansing's blog. So the older ones of you might still remember this. This was 2016. And Brian Wansing was a researcher in the food, and he had a lab called the Food and Brain Lab at a very reputable university. And he wrote this blog post. And so he described his work with a graduate student. He actually contrasted two graduate students, like a good one and a bad one. And this was the good graduate student, the grad student who never said no. In itself, that's a little bit, problematic. But what he said was, when this grad student, the good grad student, arrived, I gave her a data set of a self-funded failed study which had null results. And I said, this costs us a lot of time and a lot of our own money to collect. There's got to be something here that we can salvage, because actually it's a cool data set. I had three ideas for potential plan B, C, and D directions, since plan A had failed. I told her what the analyses should be and what the table should look like. And every day this grad student came back with puzzling new results. And every day we would come up with another way to reanalyze the data with yet another set of plausible hypotheses. So this is what he wrote in 2016, not knowing that actually what he was describing was p-hacking. So he got a lot of criticism for this. And as far as I know, even some of his studies got retracted. So basically, what they were trying to do here was actually good science, to make the best possible use of an expensive data set. But they ended up using a questionable research practice. And this, of course, I mean, it's a senior researcher, he might have known, but he may as well not known. So for the future, so that you know what it is, if you run into p-hacking, I'm going to give you a definition of p-hacking, and this is a very common definition from a paper from Simonson from 2014. See, that this paper was published before the blog post, so he could have known. And so this definition is: a researcher may run a regression with and without outliers, with and without a covariate, with one and then another dependent variable, and then only report the significant analyses in the paper. So this is exactly what Brian Wonsink and his students were doing. They were like trying to find these significant results. And this is a very common definition of p-hacking. It's a definition by example. So p-hacking is, for example, this, or this. And we tried actually to find a general definition of p-hacking, but pretty much all that is in the literature says, well, p-hacking is to use some p-hacking strategies to obtain a significant publishable result. And so we decided to call these practices that are mentioned in those definitions p-hacking strategies. And a strategy here is just an action performed to achieve something. It doesn't necessarily imply an intention of cheating. So you're the thing that you achieve might just be, for example, getting a publishable result. Now here there are three p-hacking strategies mentioned: running an analysis with and without outliers, with and without a covariate, with one and then another dependent variable. So you've got three distinct p-hacking strategies. But if you look into the literature and you look at all the papers that mention p-hacking, actually there are far more p-hacking strategies than just those three. So we tried to, in our paper, to get a semi-comprehensive list of all the p-hacking strategies that could be applicable to any analysis. And we came up with this list, and this is basically just born out of our own frustration with the definitions that were there, that were ever only so partial. So we hope that this gives a bit of a wider view on what actually constitutes p-hacking. So we've got the three strategies. Yeah, okay. We've got the three strategies here from the definition. So selective reporting of the dependent variable, which would mean that you've got multiple dependent variables and you conduct the analysis with each of those variables. We've got outlier exclusion. That means you have different exclusion criteria for outliers. For example, you exclude the 5% most extreme values, or the values that fulfill a certain, are above a certain cutoff of Cook's distance or something like this. Controlling for covariates means like you introduce covariates into your analyses, and these might be correlated with each other, correlated with the dependent or the independent variable. There are other strategies are, for example, selective reporting of the independent variable. So let's say, for example, you have multiple. So this would typically be you have multiple experimental groups and one control group, and you only report sort of the comparison that became significant. So for example, you've got different interventions, different therapy approaches, and only report the one that became significant. Optional stopping, I think most of you are probably also familiar with. Optional stopping means collecting data in batches, and then after each batch of data, reconducting the significance test and checking is it significant? If yes, stop the data collection. If no, continue collecting data until eventually you find a significant result. Scale redefinition is mostly something used in questionnaire studies where, let's say, for example, you correlate a psychometric questionnaire with something like an inventory, let's say, for anxiety or for depression, but then you might notice, oh, actually, this doesn't correlate, don't have a significant result, but maybe it's because actually my scale wasn't properly defined. So you throw out some items and recorrelate the leftover items or parts of the scale, for example, with the criterion. To be fair, I think this is mostly used for scales that are not very well established, but it happens more often than not, especially with subscales of questionnaires. Variable transformation, just, oh yeah, there's a question. Good question. If they had planned it before the analysis, would it still be p-hacking? No. So p-hacking usually means unplanned comparisons based on a non-significant result. Variable transformation means we look at, so this is something that is often being done, for example, with response times, that you log transform response times rather than taking the absolute or the untransformed values. But you can also think of other transformations, for example, log transformations, if you've got like very large data, like very large data points, or yeah, pretty much any function you can apply to your collected data. You might be familiar with discretizing variables, something like a median split, a tertile split, something like this, or a median split, but then leave out the middle group, so just compare the extreme groups. Exploiting alternative hypothesis tests, that just means like you conduct an alternative test, for example, a non-parametric test where you could conduct a parametric test, or let's say multiple contrast analyses instead of an ANOVA, something like this. Favorable imputation. Imputation means like if you've got missing values in your data sets and you replace them with plausible values, that is imputation, but obviously you can make that very favorable so that eventually your results will turn out significant. Then we've got subgroup analyses. That's something like, let's look at this effect in men and women separately, people who are right-handed and left-handed separately. So you split up your data set into categories and you check, oh, does it actually happen in this subgroup? Does the effect happen in that subgroup? And as you said, like this might be completely plausible, like a priori, but like the point about p-hacking is to do this after the fact. So your main analysis where you didn't want to look at subgroups was not significant, and then you decide, oh, but maybe actually I'm looking at this subgroup, I'm looking at that subgroup, and I'm looking at that subgroup. The last one is a bit of an odd one out, incorrect rounding. This is something that you can actually see in papers, and Michelle Nelson is also speaking, right? So she'll tell you more about this. So sometimes researchers get a p-value of like 0.0501, and then they're like, yeah, this is smaller than 0.05. This is fine, which obviously it's not, but and you can actually see this in the papers, which is something that makes this p-hacking strategy different from the others, because you can actually, at least for some of the examples, retrospectively see it in the published papers for a single test result. Okay, there was one more question over there. Yeah. Yeah. That's a very good question and leads to the next slide. So why is all of this p-hacking? Well, p-hacking leads to an increase in false positive results. That means falsely rejecting the null hypothesis, falsely saying that the alternative hypothesis is true if actually the null is true, falsely saying that there is an effect when actually there is no effect. And the reason for why this happens is alpha error accumulation. So the more tests you conduct, the more likely you are to make a mistake in one of them, and to falsely conclude that there is an effect when actually there is no effect. And you can see this. So if you were planning this in advance, it would be good practice to correct for alpha error accumulation. So to do something like Bonferroni corrections you might have heard of. So basically anything you would do for, like, let's say post hoc tests in ANOVA. But if you do this after the fact and you conduct a whole bunch of analyses, your alpha error won't be corrected, and you will have an increase in false positive results. And what we were trying to look at in this paper was actually how bad is it, and are all of these p-hacking strategies equally bad, or some maybe less bad than others. And so in the paper we did this for all of the 12 strategies, but I'll only show you these 3 here. And you can see that, well, it can get pretty bad. So let's look, for example, at outlier exclusion. So to remind you, this is using different outlier detection methods, throwing out different values as outliers depending on different outlier detection methods, and to eventually get a significant result. And the different lines here are different sample sizes. So what if we do this in a small sample, in a medium-sized sample, or in a big sample? You can see that this ranges from like 30 to 300 per group. And we've got like 3, 5, or 12 outlier detection methods. And with 12 outlier detection methods, we're at about like somewhere between 20 and 30% of false positive results. That means all of these were simulated under the null hypothesis. Actually, the null hypothesis is true. There's no effect. But nonetheless, if we use a large number of outlier detection methods, then we will still conclude that the null hypothesis is false. We'll reject the null hypothesis in more than 20% of the cases. Now, you might think like 12 outlier detection strategies is like maybe a little bit too much. Who does that? But even if you look at just 3 different outlier detection methods, you're still at like 15% or so. That's non-negligible. That's still 3 times as high as our nominal alpha level of 0.05. So 3 times as high as the 5% we'd usually accept. Essentially, this is the same for all the strategies we've looked at. Like if you are sufficiently like if you p-hack sufficiently severe, if you conduct strong p-hacking, so for example, if you use like a lot of covariates, if you use a lot of dependent variables, then eventually your false positive rates will go up through the roof. Interestingly, and I think this is something that is particularly interesting for people who work with large samples, with panel data, for example. Large sample sizes do not help you here. There's basically no p-hacking strategy that protects, like no p-hacking strategy where a large sample size protects you against the effects of p-hacking. So you can't go like, oh, but I've got this huge sample, I won't ever be able to collect it again. Well, if you p-hack, it will still have an effect. Well, so I think this pretty much explained why p-hacking is a questionable research practice. If you just p-hack enough, pretty much anything can be intentionally made significant, intentionally or unintentionally, through just trying to find the effect in your data. This also means that if enough people p-hack, this will lead to the publication of a lot of false positive results in the literature, which has also been mentioned a lot of times here in articles like these, like that gained a lot of attention. Of course, this also contributes to the low levels of replicability that we see across disciplines, actually, because if so many of the published effects are actually false positives, then we cannot expect to be able to replicate them in another experiment. Okay, I already showed you a little bit about the simulation results that we conducted, but I want to show you how we did those simulations so that maybe in the future you can run them yourselves. And it's actually a pretty simple recipe that you can pretty much apply to any problem that you have where you ask yourselves, but what would happen if people did this? And it's called a Monte Carlo simulation. And the recipe is as follows. You need some type of data generating process. Here under the null hypothesis, because we're interested in what is the effect on false positive results. So for example, you might have 2 groups, each of 100 participants with normally distributed data, same means, same variances, it's a null effect. So for example, this might be 2 groups tested on an IQ test. Then you need a statistical testing procedure that you want to apply. So for example, here with our 2 groups, this could be an independent samples t-test. And here we want to simulate p-hacking, so you need a p-hacking strategy. So you might think of, let's say, for example, 5 dependent variables. These dependent variables are correlated at 0.8. So for example, these could be different IQ tests that people are tested on. And then you use your machinery, like you may use R or Python, for example, and you use a random number generator to draw a large number of samples, including like variations, so not every sample is the same. So for example, here we draw 100 and 100 observations per group from 5 variables that correlate at 0.8 and repeat this a large number of times, let's say 10,000 times. So one data set that you get would look a little bit like this. You've got the groups here. You've got like group 1 and group 2. And then you've got 5 dependent variables, each of them one variable that these groups could potentially differ on, but as you notice, we didn't simulate any group difference here. So in reality, these are sampled from a distribution where the groups don't differ. However, the dependent variables themselves correlate pretty highly, like let's say, for example, because they are measuring the same construct. Well, and then you've got 10,000 data sets like this, and now you analyze the results. So things you can look at are the false positive rate. So for example, that will be 12.83%. That gives you the proportion of significant results if somebody tries out 5 dependent variables that are correlated at 0.8. You can, of course, also check what would happen if we didn't p-hack, and then your false positive rate here should be at around 5%. It's never exact. That's just because same as with any sampling-based method, you've got some noise in the data, and this is called a Monte Carlo error. So you can see from this approximately how close you are to the true false positive rate. So this gives you an indication of what would be the proportion of false positive significant results if no p-hacking took place, so only one dependent variable was used. You can also look at your results in terms of effect size. Here we have R squared, so the proportion of explained variance. And we can see that with p-hacking, there's this little hump in the data. This is where basically the p-hacking was effective, and we see that our effect size estimate is also affected by p-hacking. You can also see this if you look at Cohen's d, since we conducted a t-test. The effect size is Cohen's, another effect size we can look at is Cohen's d. And you can see here, it was a non-directional t-test. So again, we've got additional modes in the distribution to the left and right, where we overestimate the effect size. Now, this is the overall distribution of p-values, and what you can see here is that if we p-hack, so that those are the orange values on top, there's like a big peak of p-values under 0.05. Oh, sorry. Oh, yeah. So you can look at the entire distribution here, or you can just look at the p-values under 0.05. If you want to run this, we've created a little Shiny app, so you don't need to program, be able to program yourself. So for all of these p-hacking strategies, you can play around with it and see how bad is it actually if I do, I don't know, 10 subgroup analyses. We also put this into an R package that you can get from GitHub. Notably, this R package does not p-hack for you. It just simulates the p-hacking results. So if you're interested in basically getting p-value distributions under different types of p-hacking, you can generate them with this R package. One thing that I want to draw your attention to that sort of came out of the process when we were like thinking about p-hacking and all the definitions and trying to simulate all of the different p-hacking strategies that were mentioned in the literature, was this p-value selection method. And we also put this as a setting in the app. And there are three options: first significant, smallest, and smallest significant. First significant means that people just select the first p-value, first significant p-value that they encounter, and then basically stop p-hacking. Smallest means that they conduct a lot of analyses, and whatever the value of the p-value is, whether it's significant or not, they always select the smallest value, so the most significant value. Most significant means that people look at, they conduct a whole bunch of analyses, and then among all of those that are significant, select the analysis to report with the smallest p-value. And all of these have been mentioned in the literature and have been mentioned sometimes as like different severities of p-hacking, or like I think it was, yeah. So like people have talked about this as a type of p-hacking strategy, but actually it's something that comes on top of the p-hacking strategy. And it influences basically how your distribution of p-values, what your distribution of p-values looks like, and how the p-values distribute under this cutoff of significance. And so if you report the first significant p-value, you'll get a distribution like this, where so you see on the top in yellow, those are the p-hack p-values. On the bottom, those are the non-p-hack p-values for comparison. You see that the distribution is left skewed, so it has like the peak on the right. You may not know this, under the null hypothesis, p-values are always distributed uniformly. So it's yeah, a uniform distribution. There shouldn't be any skews to the left or to the right. So if people just report the first significant result, we often get a distribution that has its peak on the right. People might also report the small significant p-value, and in this case, the distribution is skewed to the other end. So we've got the peak of the distribution is on the left. Same if the smallest p-value is reported, then also we see that the distribution peaks on the left, so it's right skewed. This is important. So this is a figure from our appendix, and what you can see here, it's a bit of a complicated figure, but like basically, this is just looking at using multiple dependent variables, so one p-hacking strategy, and using either one, so no p-hacking, 3, 5, or 10 dependent variables, and looking at the entire p-value distribution, either with these violin plots or with what is basically a p-curve plot. And what you can see here is for every severity of p-hacking, so using 1, 3, 5, or 10 dependent variables, within this this column, basically the percentage of false positive results is always the same. So no matter how I select the p-values, if I use 10 dependent variables, the proportion of false positive results is always the same. However, it does affect, so the p-value, we call this reporting strategy, does affect how the p-value, what the p-value distribution looks like, how they the p-values distribute. So, for example, here with these two reporting strategies, you see that there is like a much quicker drop after the 0.05 value. But here, with like if people just select the smallest p-value, we've got a much smoother curve. And this leads to kind of a new project that we started around this, that all started out with Beth. She did her PhD on a project on p-curves, and she emailed me like a couple of months ago, and she was like, I read your paper and Appendix E was fantastic. And if you do, if you've been in research for a while, you know that this is very rare occasion, because you publish papers under the assumption that nobody ever reads your appendices. So I was like, oh, you read our appendices, that's great. So we started talking about this, and she said like, hey, this was actually quite interesting to see, because I've been working with p-curves, and p-curves, if you're not familiar with it, are a tool to look at the distribution of p-values below this 0.05 cutoff. And people have been claiming that, well, if they are left skewed or right skewed, then you can say something about whether questionable research practices were used in an entire literature. And so we started looking at, in this project, so this is also with Hannah and Samin, and again, Felix. We started trying to investigate p-curves through the lens of p-hacking simulations. So this is a typical p-curve where you only look at the p-values under 0.05, so under the cutoffs of significance. And you look at how many percent of the significant p-values fall within each of those intervals between 0 and 0.1, 0.01 and 0.02, 0.02 to 0.03, etc. And then you get this curve, and it can be either like it can be flat. Let's say if there was no effect whatsoever, it should, and no p-hacking took place, it should be flat. It should be uniform, because p-values are distributed uniformly under the null hypothesis. Or it can be like it can have a peak to the left or to the right. And this peak can be indicative of like true non-zero effect sizes in the literature, or it can be indicative of questionable research practices. And the question is, can we somehow figure out what happened here? Like, how did we get to a distribution like this? And this one here is based on a data set from Wetzels et al., where they looked at 855 t-tests across experimental psychology. So the field is pretty big. And it's 2011, so we would expect that people didn't really know about p-hacking. And if you look at a p-curve like this, basically what could have generated them are sort of three possible worlds. You can have a worst possible world where there's no effect whatsoever. There's basically no effect in experimental psychology, which we hope is not the case. But theoretically, this could be the case. So the effect size is 0 for all studies. All effects that we would see would be because of p-hacking or questionable research practices. We could also have a perfect world where effect sizes are always there, or like some studies have null effects, some studies have true effects, but most importantly, nobody p-hacks. Or we have a realistic world where sometimes there's an effect, sometimes there's no effect. Some people p-hack, some people don't p-hack. And what we did was to look at a whole bunch of simulations. So rather than just looking at what we did in our initial simulations, what would be the effect of having, like, let's say 5 dependent variables? We looked at many different scenarios. So for example, for the worst possible world, we said, well, the effect is 0 for all of the studies. However, we look at all different severities of p-hacking. We did only look at one p-hacking strategy, which was using multiple dependent variables. But because this is still quite preliminary. But then what we did is to look at which one of these simulations gets closest to the actual empirical p-curve. And then we can look at those simulation conditions and get an idea of what might be happening if we were in this case, worst possible world. So what you can see here is in black is the original p-curve, and in blue is the one that we got from our simulations. And you can see that they're already like reasonably close. So the one here is generated from a world where 20% of researchers p-hack, and they p-hack with like an enormous number of dependent variables. So here, 148 uncorrelated dependent variables. And if you remember from before, like correlation between dependent variables influences how grave the effects of p-hacking are. And with uncorrelated variables, you increase the alpha error the most. And they all selected the smallest p-value. So this is like if there was no effect whatsoever in the literature, this would be the most likely scenario that would have happened. In the perfect world, it looks like this, and you can see that our sort of best simulation fits much better here. So this is nobody p-hacks, but in the best fitting simulation, the alternative hypothesis was true in 50% of the cases. 50% of the studies had a null effect. And if the alternative hypothesis was true, the effect size was pretty large with 0.7. Plus minus 0.1, we simulated some heterogeneity between effect size because it's really unrealistic that every study would have the same effect size. Now to the realistic world, and you can see, you can basically not see the blue line here. And this means that our best fitting simulation was actually really close to the observed data. So here the best simulations show that 20% of researchers p-hack. The alternative hypothesis, again, was true in 50% of studies. And if the alternative hypothesis was true, the effect size was 0.5, so, which is approximately a medium effect with some heterogeneity. And if people p-hacked, again, they p-hacked a lot with like 200 dependent variables, all correlated at about 0.3, and they selected the smallest p-value. So you might think, okay, hey, I can actually make inferences from this p-curve about what people did. That would be really, really cool. So is this really what people did in the experimental psychology literature leading up to 2011? Did we really have like 20% of people who p-hacked with like 200 dependent variables? Well, it's not that easy, unfortunately. And I think this also speaks to the difficulties with interpreting p-curves, which might be something you might run into if you're doing something like meta-science. So here I plotted our 10 best simulation results. What you notice is that you still basically can't see the blue lines. So all of these 10 blue lines are basically on top of the real world p-curve. But if you look at the simulation conditions that generated these 10 blue lines, they're actually quite variable. So we've got something like between 20 and 80% of researchers p-hacked. 40 to 50% of in 40 to 50% of studies, the alternative hypothesis is true. If the alternative hypothesis was true, the effect size was 0.5 to 0.7 with a little or with no to a little heterogeneity, but like something like p-hacking severity between 2 and 200 dependent variables. So that's a lot of variation. Also correlated at 0.30 to 90. That's a huge variability in the potential severity of p-hacking people did. And people might also be selecting the smallest or smallest significant p-value. So like we actually, within these 10 best simulations, we've got a huge variability in possible worlds that may have generated this exact p-curve. So many different scenarios, many different simulation scenarios can actually create almost identical p-curves. We can also see that right-skewed p-curves, so like with the peak on the left, like this one, can occur even in the worst possible world. And they're not, which some people say, indicative of high power and non-zero effect sizes. With the simulations, there are lots of different possible scenarios that could have generated a p-curve, but actually there are also some scenarios that are like really, really, really far off. So at least there is some way of using the simulations to distinguish what are more and less likely scenarios that could have happened. So it's kind of a like pro and con finding, I'd say. In our case, I showed you that the most complex scenario, so the realistic world, fit the pre-replication crisis data set the best. And well, this is kind of unsurprising because one, just from a mathematical perspective, the more free parameters have, the more complex your model is, the better it can usually fit empirical data. So this is the next step we're going to do. We're going to look at like to what extent can we somehow punish for model complexity here. But also the fact that the most complex model fit the data the best is not really surprising because it just makes the most realistic assumptions. Probably not everybody p-hacks with like 200 dependent variables because just not everybody has the time. So it's really it's quite a realistic scenario. Obviously, especially the last the new project is still very much a work in progress, but I think there are a couple of take-home messages here. So first of all, you can see from the results and from the simulations that p-hacking is a questionable research practice that does increase the probability of false positive results. So if you look at all of these different p-hacking strategies, basically with any of these strategies, you can get a false positive result if you just try hard enough. We can use simulations to explore the effects of p-hacking and also other questionable research practices. So whenever you think that something might be a questionable research practice, I encourage you to go out and try and simulate it. And if you feel like, oh, I'm not really sure how to do it, find somebody else who has done a simulation before and try and collaborate with them. And this is really a good way of finding out whether your methodological approach is a good one. P-hacking strategies are distinct from p-value reporting strategies. So this is something that is often confused in the p-hacking literature. So you will read about these reporting strategies, or like strategies, smallest significant, smallest p-value, or first significant p-value, often as part of a p-hacking strategy, but actually they're quite distinct because the p-hacking strategy itself determines the type 1 error rate, but the reporting determines the overall distribution. Both p-hacking strategies and p-hacking reporting strategies, p-value reporting strategies can influence the p-curve. So if you look at p-curves that have been published about some literatures in the past, and they make some conclusions about whether p-hacking took place, whether questionable research practices took place, keep in mind that there are many different possible scenarios that could have influenced the p-curve as you see it. Yeah, and I think that's it for me for today. I'm looking forward to your questions. There is a question up there.
Yeah. We have people with driver mice there with us.
First of all, thank you very much indeed. I thought that was really, really exciting. And the graphs and the simulations. I was wondering, when do you think people started identifying p-hacking? Because it wasn't always called p-hacking. This is a sexy new title, isn't it?
Yeah.
It was probably called something else before, like maybe non-reproducible data or results or something like that.
Yeah.
And I went to I did a course at Oxford University on it was called reproducibility and credibility, and the idea is for people to try to reproduce. That used to be the old way, but now everybody tries to have an original paper, so they don't really go so much for trying to reproduce material. So I know at the beginning you kind of like said this, but I think it was well before then. And I'm just thinking, if there had been, in your opinion, maybe it's become more sexy to talk about it, giving it this new name and things like that. So what was your view? And also, what got you into it as well?
Yeah, so I just scrolled back to this slide because this is one of the first occurrences of the term p-hacking that I'm aware of. Not because it wasn't there before that, but just because I couldn't remember the year of the paper. So the term p-hacking has not really been used before, like let's say 2013. So this paper was pre-printed before. So I think it came up around that time. But before that, you're absolutely right. People have been talking about alpha error accumulation. They have been talking about even something like, I love the term data torture. And so the earliest mentions of that I am aware of come from like the 60s. So for example, there's a nice paper from, he's called Armitage, I'm not sure how to pronounce it, on the effects of optional stopping. And I'm pretty sure that like that paper already mentioned optional stopping as such, just didn't say this is one p-hacking strategy that people could use. Just like he showed what the effects of optional stopping could be. And that was from, I think it's like 1969. So like, yes, this predates a lot. So yes, and also something like Bonferroni correction was around, right? So people have been thinking about alpha error accumulation way before that even. So in that sense, I think it has been on people's mind. And the idea of, okay, so I do like, let's say an ANOVA, and I do post hoc tests, and they're exploratory, and I do a whole bunch of them, and that this at some point raises the false positive rate, I think was on people's minds. But things like outlier, like different outlier exclusion methods, or favorable imputation or something, are ideas that only came up later in the process, and are, I think, also something that people are even today not so much aware of, that this can constitute p-hacking. And again, it doesn't always, like pre-registration helps, but if it's driven by the idea of getting false, or getting positive, getting significant results, then we should get cautious. Does this answer your question, or would you like me to comment on some? Pardon, what?
But was just a naughty person all through and through, or was actually a p-hacker?
Whether I know personally someone who was p-hacking.
Cyril Bird, did you say? Yeah. Well, if you want to learn more about Cyril Bird, you can look at last year's summer school, because we actually had Tony Pelosi talking about Hans Eysenck, who obviously worked with Cyril Bird. But I think this is where the line between deliberate intentional fabrication and p-hacking, that line gets a bit blurred. But I will just hog the mic a little bit. I can't speak to statistical techniques to spell out the effect of p-hacking or the many different forms. But the earliest reference I'm aware of where the idea of p-hacking is described is 1830 by Charles Babbage, in a book titled Reflections on the Decline of Science in England. So it's obviously a conversation we've been going on for 200 years now, where he talks about this idea of cooking the books. And he, in very 19th century language, basically puts it as when you have lots of different observations and you just pick the one that fits just so, so cherry picking. But that's the earliest I'm aware of, but I'm sure this has been going on since people's reputations were tied to their scientific output. I think there's one question, is why you got into this, Angelika. Angelika, the one question that I'd asked about was also why you got into this. Was it just an itch that you needed to scratch?
Well, so originally we planned to do something more like p-hacking detection, right? So like basically what we're going towards now again. So our original project idea was like, hey, actually we could like somehow simulate p-hacking and maybe find a way of detecting it. But then I looked into the literature and I was like, okay, so what is p-hacking actually? And then stumbled across all of these like partial definitions, and then I felt like it was not very well defined. And obviously, like, p-hacking is one of the most prominent questionable research practices out there, that everybody seems to be talking about, and that it like is featuring in every introductory lecture on reproducible science and on the replication crisis. So actually, for me, it was like, I didn't originally want to write this paper. It was more so, I was a bit shocked at how underdefined one of the most commonly used terms in sort of the meta research community actually is. And so I started looking at all of these definitions, and then started thinking about, okay, so what does it actually mean if we p-hack like this way or that way? So it's almost like, I think this project came out of my frustration that I felt like p-hacking wasn't very well defined, and we actually didn't understand it as well as we could do. Now, for like my personal motivation to get into the like open science and meta science community in general, I think I've just seen the effects of it. So I'm old enough that during my first like I had a research assistant position, and I was basically told, like, yeah, so you conduct this experiment, and like every 5 participants or so, you come to us with the results, and then we'll run some analyses in the background, and then we'll tell you whether you should be keep collecting data or not. And I was like, okay, yeah, this sounds interesting. Obviously, like, kind of first year undergrad did that, but then heard about like how bad actually optional stopping is, and then I went like, oh my god, what did I do, right? And that kind of got me into the entire like open science and meta science, reproducible science community, because I started questioning what people are doing, and whether everybody knows exactly sort of how bad it is sometimes, what like how bad the ways are in which they are trying to do research.
Brilliant. I'll take a question from online first before we go back to the floor here. But anybody else online, please do feel free to add more questions in the chat. So stuck to a cable. The question is, do you think p-hacking would happen less frequently if we start being transparent about exploratory studies? I have a feeling we have an exploratory attitude at the beginning and then publish it as a confirmatory study.
Yeah, I think this is a very good question, and also something I originally had it on the slides, and I was like, yeah, something that obviously, like, all that I showed you, all the simulations cannot tell us is what interventions would be successful to avoid p-hacking, to make fewer people p-hack. And I think in sort of increasing the value and the acceptance of exploratory research is definitely one of them. So if people were allowed to just report, okay, we did this entire bunch of analyses because we didn't have strong hypotheses, or we had a strong hypothesis, well, it didn't turn out that well, but now we did a whole lot of follow-up analyses that might be able to explain what's going on, knowing fully well that we'd have to test them in a separate data set to get convincing evidence again. I think that's a perfectly good idea. I think in terms of p-hacking, one challenge that I see in this regard is that even when people are doing exploratory analyses, they still use p-values, right? A lot of people would still say, like, I'm conducting this t-test as like an exploratory subgroup analysis, but then report the p-value and interpret everything as if it was confirmatory, just saying that it was exploratory. So I think there is some need of like good exploratory methods that could like almost replace the p-value, because I think there is some danger that we label things as exploratory, which is good, which is an advance, but then still in the end, in the interpretation, pretend that they were confirmatory. So there's some need to develop like good guidance for how to do exploratory analyses too.
Very good. Whilst I'm walking, I have one question, so I'm going to use my privilege as chair and ask, can your simulation extend to account for people that fiddle with their data, that maybe fabricate, whether that's, you know, duplicating a certain percentage of their data set or swapping participants around?
No, we intentionally did not include any fiddling with the data that could not be like an actual analysis strategy. So I think we discussed this especially with outlier removal, because I think there it's especially like visible, or like it would be the most likely that you just go like, okay, let's try and exclude every value. But no, we didn't do it because we generally try to keep the assumption that people might be doing these things unintentionally. And I think something like deliberately adding data values, for example, that like deliberately faking individual data values that would create a significant result, or deliberately deleting one or like something like half the data set or something, if it's not within one of those like analysis strategies, like we don't think that this would happen unintentionally anymore. And I think then we're like trespassing into like fraud territory, which is something that I think p-hacking in itself is not necessarily a part of. But obviously it's like up to discussion and definition.
Sorry, I've got first one observation and some questions. Very good point that you brought up is that years ago when I had some interaction with scientists, lecturers, so-called, with reputable universities, and what they did tell me was that they were paid by big pharma companies to do certain research with certain outcomes which they would like. And that's the norm, because universities need the money, the scientists need the funding to continue with what they're doing. And that's why I read a research paper with such skepticism. But now this coming on from a few years on, when a paper is published in a journal, is it checked? I know they're usually, you know, they do various checks, etc. How clear is the checking process? And does it mean that papers like, let's say from 2020 onwards, would have a better standard or compared to previously, or has nothing changed? What you said about p-hacking and intentionally changing numbers or closing an eye to numbers, where does that stop?
Very good question. So a couple of observations. So one, it is actually it's basically impossible to figure out whether somebody in a single paper did engage in p-hacking. At least if you don't have access to the original data, you just got to believe the people. So what you see in like sort of the post-replication crisis area versus the pre-replication crisis area is that you've got way more like admitted p-hacking in papers than after. So for example, that people actually mentioned something like, we got a bunch of non-significant results, and this was the only thing that worked, is way more like that. Somebody actually writes something like this in the paper is way more common before the replication crisis than after. Does that indicate that people do this less in like the past couple of years? I don't know. Maybe they just learned, okay, this is something that I shouldn't report. Or the reviewers pick up on it and say like, look, what did you write here? And then they just delete it. So we don't know exactly what happens, whether those practices decrease. We know a little bit from like survey studies, and it looks like questionable research practices decreased over time since they became more well known. Of course, that could also be like some social desirability bias in surveys. When it comes to checking individual papers, I think the best thing you can do for an individual paper is to check for transparency rather than to try and figure out whether p-hacking took place. So some people, I know that some people disagree with me here. And again, I'm not talking about instances of fraud or like data, like fiddling with the data, because those can be detected. But I think like some people go and read a paper and they read, I don't know, like they conducted 5 analyses, and in every analysis the p-value is just below 0.05. So they're like, oh, this must be p-hacking. But after conducting all of these simulations, honestly, my opinion is just it can happen, you know. And what I really don't want to do is to just accuse people of intentionally p-hacking their results when actually they didn't even p-hack, and it was just this can just happen by chance. So I think the best thing to do is to make everything as open as possible, to make the data open if possible, to make the analysis code open if possible, like that should usually be possible, and allow for as much post-publication scrutiny and criticism as possible, to allow people to investigate like the same phenomenon with other methods, to allow people to reanalyze the data using the same code or different code to just make things reproducible, because at least that way we can see whether, like, let's say other results would have been possible in the sense of like sensitivity analyses, for example. Yeah. Does this answer your question?
Okay, I think we have time for one last question.
Hiya. So I'm not as well known to all of this. It's all brand new. But my question is, if it has so many issues, why is it accepted? Why isn't it being removed? It's coming from a different perspective, but it shouldn't be there if your people want to scrutinize it and look at it. And why is it there? Shouldn't just the p-hacking be something that just doesn't exist anymore? Or is it just a perspective I'm not with everybody else? I'm just seeing there's no point.
So I think this again sort of plays into the question of how often does it happen anymore? And I think it probably still happens more often than we think it does, even with people who are familiar with p-hacking, because if you're like in the weeds of your own study and you're just interested in like what is happening in your data, it's very easy to lose the sense for like, am I just exploring my data, or am I p-hacking, and how do I report this? So I think It's very easy just to unintentionally get lost in your data, which is, I think, the most common occurrence of p-hacking. I think it probably also still happens intentionally. There's a lot of pressure on researchers to publish, and it's still the case that we have publication bias, and that significant results get published easier. So I think, yes, it definitely still happens. It may happen less than before, but yeah, it's probably, we're far from extinguishing it as a practice, and I'm not sure if we ever will, to be honest.
Brilliant. Well, one more round of applause for Angelika.